To understand word embeddings, we need to recall some basic mathematics, right? So we're going to recall some stuff from linear algebra and some stuff from abstract algebra, from group theory, so that you learned in the course of groups and symmetries. So the dot product, to compute the dot product of two vectors, we just multiply their corresponding entries and then add everything together. So here is an example. So here we have this vector is 1, 2. This vector is 3, 1. To multiply them together, we multiply 1 and 3, the first entry, 1 times 3, plus we multiply the second entries, 2 times 1, and the answer is 5. It is a scalar. So at the same time, it is known that the dot product of two vectors is the product of their norms multiplied by the cosine of the angle between the vectors. So to find the norm, we just take the dot square of a vector and take the square root. So which means that in order to find the cosine of the angle between the two vectors, we multiply, find their dot product and divide by the product of their norms. For example, for these two vectors, 1, 2, and 3, 1, the norm of the first vector is going to be the square root of 1 square plus 2 square, which is square root 5. The norm of the second vector is going to be square root of 3 square plus 1 square, which is square root of 10. Right, so the dot product of these two vectors is 5, as we have already calculated. So 5 divided by square root of 5 times square root of 10. Well, and then I guess we can simplify it. 5 divided by square root of 50, right? So 5 divided by square root of 2 times 25, which is 1 over square root 2. Okay, so vectors pointing in the same direction have cosine similarity of 1, and vectors pointing in the opposite direction have cosine similarity of -1. So, and orthogonal vectors have cosine similarity 0. So if two vectors are perpendicular, then the cosine similarity is 0. Okay, now we need to review some group theory. So a group is a set together with an operation. We can denote this operation by star, but it can be any operation, can be addition, can be multiplication, or can be anything, well, anything that you can come up to with, so you, in any case, the operation is supposed to be associative, that there should exist the identity element, and for each element that there should be an inverse element. So these are the three properties defining a group. So let us look at a couple of examples of groups. So first example, the group is going to be the integers with the addition of integers being the operation, right? Now, why is this a group? So first, is this operation associative? So A plus B plus C equals A plus B plus C. Yes, correct. It is associative. Well, since here my operation is addition, it means that I'm going to replace the star with the addition operation. So what is the identity element? Something that if you add it to anything, then it doesn't change the result. It should be 0, right? Because x plus 0 equals 0 plus x equals x. So my identity element is 0. And what is the inverse element? So the inverse element should be something that if you add to x, then you get the identity, which is 0. And this is negative x, right? Because if you add x and negative x, you get 0. And same is if you add negative x and x. Okay, so another example. SL2 of Z. So this is the set of matrices A, B, C, D, such that all the entries are integers. A, B, C, D are integers, and the determinant is 1. So A, D minus B, C is 1. And the operation here is just the matrix product. Now, notice that in the first example, my operation addition is not only associative, but it is also commutative. So such a group is abelian. So SL2 of Z is also a group because the multiplication of matrices is associative, but it is non-commutative. Okay, so what is the identity element? So the identity element here is the identity matrix 1, 0, 0, 1. If we multiply anything by the identity matrix, we get the same thing. And the inverse matrix is, so notice that, well, generally speaking, to calculate the inverse matrix, we should divide by the determinant of A. So we take the cofactor matrix divided by the determinant of A. But here, in this case, the determinant of A is 1. So which is why if our original matrix was an integer matrix, then the determinant, so then the new matrix is still an integer matrix, and the determinant of the new matrix is still going to be 1. So which is why the inverse matrix is still in the same set. So which means that the third axiom is fulfilled. Okay, so a homomorphism is a function from one group to another group that preserves the group operation. So what could be an example of a homomorphism? So let me give you the following example. So my G is going to be the group of real numbers with addition, right? And the identity element is 0. My G1 and my G2 is going to be the group of 2 by 2 matrices with real entries, and the operation is also addition. So, and with respect to the addition, the identity element is the 0 matrix. Okay, and my homomorphism is going to be phi of R is going to be the matrix R, 0, 0, R. Right, so now if I compute phi of R, well, my star is plus, so R plus S. Then this is going to be R plus S, 0, 0, R plus S. This is R, 0, 0, R plus the matrix S, 0, 0, S, which is phi of R plus phi of S. And this works because my operation on G2 is also the addition. Okay, so please do the quiz now.